Hello, this is the MA 16010 Spring 25 Exam 3. Problem 1. Problem 1 says, for which of the following is the limit as x approaches infinity of f of x equal to negative infinity? And in this scenario, all of our options are rational functions. So the reason I bring that up is before we look at the problem, I'm just going to quickly go over the rules for rational functions. So rational functions basically means any function where your numerator and denominator are both polynomials. So we have three scenarios, I guess. We have top heavy, equal, and then bottom heavy. Okay, and so when I'm referring to top heavy, basically what we want to consider is we want to consider the largest degree, the largest degree of the polynomial in the numerator and denominator. Okay, so an example of a top heavy function would be like x cubed over x, because the 3 is greater than the 1. So we have degree 3 on top and degree 1 on the bottom. So since 3 is bigger than 1, we call this top heavy. Equal would be like x squared over x squared. And then bottom would be if our polynomial on the bottom had a bigger degree polynomial. Okay, and then the other thing I just want to quickly bring up is it doesn't matter how many terms you have. So I could have like x to the power of 4 plus x cubed plus like other stuff. And in the bottom, let's say I have x to the power of 100 plus x to the power of 9 plus, I don't know, 99 plus like on and on. None of this matters. All you have to do is you have to consider the two largest degree polynomials and compare those two. Okay? So, yeah. So if we have a top heavy function, our limit as x approaches 0 or x approaches infinity or negative infinity is always equal to 0. If we top heavy, I mixed this up. So if we have bottom heavy, then the limit as x approaches infinity is always equal to 0. Same for limit as x approaches negative infinity. It's always equal to 0. If we have top heavy, then if we have top heavy, then it is equal to either negative infinity or positive infinity. It depends. And then the same applies for x approaches negative infinity. It's either gonna be positive or negative infinity, and I'll talk about how we can discern that. And then if we have an equal heavy function, then what we have to do is we have to consider the coefficients of the largest degree terms on both the numerator and denominator, and we take the ratio of that. So again, plus or minus depends on whether we have x approaches infinity or x approaches negative infinity and like different things. So I'm just going to abbreviate this as CA over CB, but it's going to be the ratio of the coefficients. So that's why I'm writing CA, CB. Okay. So those are our rules. And in this case, we are told that our limit as f of x approaches infinity, as x approaches infinity of f of x is negative infinity. And so the only scenario where we can have positive infinity or negative infinity is a top-heavy function. So we know f of x is top-heavy. So this means that we can rule out a couple options. First of all, we can rule out A because our largest degree components are the degree of the top polynomial is 1 and the bottom polynomial is also 1. And one thing I want you to notice is that they've intentionally ordered these polynomials weird, where they've, instead of putting minus 5x plus 10, they've switched it around to mess with you, so that's also something to be aware of. Okay, similarly, B is also incorrect because we have degree 1 on top and degree 1 on bottom. C is a possible answer choice because we have degree 2 and degree 1 on the bottom. So 2 over 1, we have a top-heavy function. D is not an option because we have degree 3 on top and we have degree 4. So I'll highlight these. Okay, I just realized. Yeah. Okay, so degree 3 on top, degree 4 on bottom. That means it's bottom heavy since the degree is bigger in the denominator. Okay, another equal heavy. This is equal heavy since we have x squared on top and x squared on bottom. Okay. Yeah, we're looking for top heavy functions. So it should be C or F. Alright. And yeah, now we have to determine whether the answer is C or F. And this is where it's important to discuss how do we determine if the limit is going to be positive infinity or if it's going to be negative infinity. And so the way you do this is plug in a positive number. So first of all, let me step back a second. We only need to consider the two terms with the largest degree. So in the denominator here, it's 9x, and in the numerator here, it's negative x squared. So negative x squared and 9x. And I'll plug in a positive number. It can be any positive number. So if we plug in 1, this is also a negative number. It's negative 1/9. And so we realize that if we plug in a positive number, the output is negative, which means if we were to plug in infinity, your output would also be negative infinity, which means that the answer is C. The reason I say plug in a positive number is technically you can't plug in a negative, you can't plug in infinity, but you could also, for the sake of understanding, you could also do something like this. Well, infinity squared is going to be a positive number, so that means that the numerator is a negative number. So I'll just say the numerator is negative. I'll just write the signs, and the denominator is positive since infinity times 9 would be a positive number. So that's how we get that this answer, this limit would be negative infinity. In contrast, if we did the same thing for f, which is negative x squared is our largest degree term, and negative x is our largest degree term in the denominator. Well, if we plug in a positive number, so I'm just going to write the signs maybe. That's another way you could think about it. So, and then, okay. Well, clearly these negative signs cancel out. A positive number squared is positive. Positive number divided by a positive number is also positive. So in this case, for this case, limit as f of x approaches infinity would be infinity as well, which is why it's the wrong answer. So the correct answer for 1 is F. All right, moving on to question 2. Problem 2 says, find the slant asymptote of f of x which is equal to negative 6x squared plus 7x minus 8 divided by negative 2x plus 1. Okay, so a slant asymptote is basically when we have a function that is approaching some line. It's approaching a line but never touches the line. So it's almost the same concept as a vertical or horizontal asymptote, except the thing you're not touching is not y equals 0 or x equals 0, etc. Okay, and you can only have a slant asymptote. You can only have a slant asymptote when the degree of the numerator is 1 greater than the degree of the denominator. Okay? And in this case, you can see that it is possible to have a slant asymptote because the degree of the numerator is 2 and the degree of the denominator is 1. So the way we find a slant asymptote is we have to do long division to split up our function into two parts, and the slant asymptote will be the value of the quotient. So I'll walk through now how we can do long division. So long division with polynomials seems hard, but it's really the same thing as normal long division with integers or something. Okay, so we always start with the biggest or highest degree term, which in this case is negative 6x squared, and I want to see what can I multiply times this polynomial to get rid of the negative 6x squared. Okay, since I have a negative 2x, what I want to multiply is a 3x. So 3x times negative 2x plus 1 is negative 6x plus 3x. So just like normal division, I multiply these two numbers together and then subtract it from the total. Okay, and if I subtract it, I get 4x minus 8. Same deal here. What do I need to multiply minus 2x times? What do I have to multiply to negative 2x plus 1 to get rid of the 4x? That would be negative 2. So negative 2 times negative 2x is 4x, and then negative 2 times 1 is negative 2. So I get negative 6. And you'll see why later, but this number doesn't actually really matter. So there's nothing else I can do now that I've reached the negative 6. There's no other polynomial term that I can multiply to get rid of this negative 6. So we're done now. And we get f of x is equal to 3x minus 2 plus negative 6 divided by negative 2x plus 1. Just in case if I wasn't clear, you always stop after multiplying, after putting a constant up here. I wouldn't multiply, I wouldn't add something over x here to try and get rid of the negative 6. Yeah. Because the value of our slant asymptote is going to be, as I mentioned before, the value of the quotient, which needs to be a linear function if we're going to have an asymptote. So in this case, since our quotient is 3x minus 2, that means our slant asymptote is 3x minus 2, which means that the answer for problem 2 is C. Okay, alright, moving on to question 3. Question 3 says, compute the sum of I squared plus 3 from I equals 1 to I equals 4. So this problem is asking us to find a summation, and just as a quick review of summations, let's say I have I equals 0 and up until n of f of I. So this is basically saying that I want to find the sum of f of 0 plus f of 1 plus f of 2, so on, so on, so on, until f of n. Okay? So same deal here. All I have to do is plug in 1 into this function, plug in 1, 2, 3, and 4 into this function, and then add up. So 1 squared plus 3 plus 2 squared plus 3 plus 3 squared plus 3 plus 4 squared plus 3, which this all should add up to 45. Okay, there's also some tricks you can do with this question using some properties of summations. So I'll write that up here. If you want to find the summation of, or actually I will write it down here. Okay, so let's say I want to find the summation of two different functions. So I want to find the summation of f of I plus g of I. Okay, we can actually split this up into two different summations. So the summation of f of I from I equals 0 to f of n plus the summation of plus the summation of g of I from I equals 0 to I equals n. And the other property is that if I take the summation of a constant, so I'll call this c, and notice that for this problem I changed the bounds from 0 to 1. So if I'm taking the sum from I equals 1 to n of some constant c, this is equal to c times n. Okay? So now I'm going to use these properties on the question in the problem because that makes things significantly easier to solve. So I equals 1 to 4 of I squared plus 3 is equal to the sum of I equals 1 to 4 of I squared plus the sum of I equals 1 plus the sum of 3 from I equals 1 to 4. Well, by this second property over here, we know that's equal to 3 times 4. And in my opinion, this is a little easier to solve because I have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 12. I think, yeah, it's about the same, but I think it's a little easier to solve. And yeah, we got the same answer of 45. Yeah. Yes, because this adds up to 14 plus 16. My bad, I made a mistake. This should add up to 42. Yeah, 14 plus 16 plus 12 is 42. So the correct answer for problem 3 is E. Okay, moving on to problem 4. Problem 4 says, find the antiderivative of sine of x minus cosecant x squared. Okay, so for this problem, we have to use our antiderivative rules. And the first thing I would do is I would split this integral up into two parts. So anytime we have an integral and things are being subtracted or things are being added, we can always split things up like this. So this would be sine of x the antiderivative of sine of x dx minus cosecant x squared dx. And from here, all we have to do is we have to use our basic antiderivative rules. So the antiderivative of sine of x is negative cosine x. So I'm just going to draw an arrow. And the antiderivative of cosecant x squared is negative cotangent of x. Yep. And so notice we have a minus minus here, so that becomes negative cosine x plus cotangent x. So really the big trick, it's not really a trick, but anytime you have these basic antiderivatives, you have to memorize them. But something I find helpful is I memorize the derivative rules and I work backwards. So I know that the derivative of cosine of x is equal to negative sine x. So as opposed to memorizing both the antiderivative and the derivative rules, I only memorize the derivative rules and then work backwards to figure out the antiderivative rules. So if I know that the derivative of cosine of x is equal to negative sine x, then the antiderivative of sine x is just negative cosine x. And in the same way, I know that the derivative of cotangent of x equals negative cosecant squared x. So the antiderivative of cosecant x squared is just going to be negative cotangent x. Yeah, like I said, you just have to memorize these. But that means that the answer for problem 4 is B. All right, moving on to question 5. Question 5 says the graph of the derivative of f of x is shown below. Choose the correct statement regarding f of x. Okay, and notice they bold derivative of f of x. Okay, and it says f of x, and basically all of the statements are stating what the critical numbers of f of x are. Okay, so first we have to understand what a critical number is. And a critical number or critical value or critical point, I've also heard, is where f of x is any point where f prime of x is equal to 0 or undefined. So in this case, our and then the critical points also, it's not relevant for this problem, but the critical points indicate possible locations for a local minima or local maxima. Okay, yeah, but in this case, all we need is this first statement over here. The critical values are located at points where f prime of x is equal to 0. And if we look at our graph, it's pretty clear. We have one critical point at f equals 0 and another critical point at f equals 4. At x equals 0 and x equals 4. So that means that f of x has two critical numbers, which are x equals 0 and x equals 4. So our answer to problem 5 is B. Okay, moving on to question 6. Problem 6 says, evaluate the antiderivative of 2 times root x plus 6x cubed plus 3 divided by x dx. Okay, So at first glance, this problem looks really, really tricky. But it's actually not that bad. And so the trick here is to notice that we have a rational expression and we only have an x in the denominator. So what we can do is we can split this fraction up as such. And so I think it's most obvious with this center term, but we can simplify 6x cubed over x to 6x squared. It's not as obvious for the first term, but 2 root x divided by x can be simplified to 2x to the power of negative 1/2. And this is because of our exponent rules. Square root of x is equal to x to the power of 1/2. So this is pretty important to understand for finding antiderivatives. Just in calculus, it's important. Okay, and then we can't really simplify 3 over x, but that's okay. So now what we've done is we've actually simplified our expression into something that we can use our basic antiderivative rules on. So for these first two terms, we can use the reverse power rule. So yeah, we can use the reverse power rule. This first term would simplify to 4 times x to the power of 1/2. And if you want to double check that you're correct, you can always do the power rule again to make sure you get the right value for this expression. Or you can derive again. Okay, the antiderivative of 6x squared is 2x cubed. And we can't use the power rule for 3 over x, but if you remember your derivative rules, the derivative of natural log of x is 1 over x. Yes? So that means that the antiderivative of 1 over x is natural log of x, which means that the antiderivative of this is 3 times natural log of the absolute value of x. Anytime we're taking the antiderivative of 1 over x, we need to do an absolute value around the expression in the denominator. And then lastly, we need to add a plus c. Okay, and then the last step we need to do is we need to rewrite x to the power of 1/2 as square root of x. Okay. So our final answer is 4 times root x plus 2x cubed plus 3 times lateral log of x plus c, which means that the correct answer to problem 6 is A. All right, moving on to question 7. Question 7 says, a family wants to fence a rectangular play area alongside the wall of their house. The wall of their house bounds one side of the play area. If they want the play area to be exactly 2,500 feet squared, what is the least amount of fencing needed? Okay, so first let's draw a picture. So this is kind of what the fence looks like. And if we say that one side is x, in order for the area to be 2,500 feet squared, the length of the other side must be 2,500 divided by x. And then, since it's rectangular, this piece, this section will also be length x. Okay, and this is the house. Awesome. Okay, so this means that the perimeter is equal to 2x plus 2,500 divided by x. And what they want us to do is they want us to find the least amount of fencing. So anytime in calculus, anytime we see least or maximum or most or minimum, what we want to do is we want to find, anytime we hear something like that, what you want to think is you want to think derivative, because derivatives can help us find the minimum and maximum values of a function. So in order to find the minimum value of this perimeter, what we can do is we can take the derivative. So I need to take the derivative of p with respect to x. So I should actually write it like this. Okay, so this is easy enough. If we take the derivative of 2x is equal to 2, and the derivative of 2,500 is negative 2,500 over x squared. Yes, okay. And the minimum and maximum values are always located at the x values where the derivative equals 0. So what we want to do is we want to set this equal to 0. Okay, and then we just use algebra to solve for x, which gives me x is equal to the square root of 1,250. Yes, okay. And so now, if I plug this in, I get the perimeter is equal to 2 times the square root of 1,250 plus 2,500 divided by 1,250. Okay, and then then we just use a calculator to calculate that. So this expression is equal to 141.4. So the final answer for problem 7 is F. Okay, moving on to question 8. Question 8 says, consider the function f of x equals x squared plus 2x plus 1 divided by 2x minus 8. And they tell us to consider the following statements. F of x does not have a horizontal asymptote, f of x has a vertical asymptote, f of x has a slant asymptote, and statement 4 is the x-intercept of f of x is negative 1, 0. And they ask which of the statements are true. Okay, so first let's consider when a function has a horizontal, like when do functions have each type of asymptote? Okay, so a function has a horizontal asymptote only if the degree of the numerator is less than the degree of the a function, if the degree of the numerator is less than degree of the denominator, then the horizontal asymptote is 0. Okay? And then if the degree, so I'm just going to abbreviate this. So if the degree of the numerator equals the degree of the denominator, the horizontal asymptote I'm going to write this out a little bit more neater. So for any asymptote case, we usually consider the largest, the degree of the numerator and the degree of the denominator. So I'm actually going to, say the degree of the numerator is n, and the degree of the denominator is m. Okay. So for a horizontal asymptote, if n is greater than m, there is no asymptote. And so one way you can understand this is relative to the denominator, the numerator is going to grow really big. So your function is going to tend to infinity. Like imagine if you have x squared as your largest degree term in the numerator and x as your largest degree term in the denominator. X squared over x goes towards infinity. Okay, I'm going to write, so if it's n equals m, the value of the horizontal asymptote is equal to, sorry, this should be y equals, because it's horizontal. That's equal to CA divided by CB, where the C is the coefficient of the numerator term, the largest degree numerator term and the largest degree denominator term. So, for example, if you have something like 5x squared divided by 4x squared, and you have like other stuff here, all you consider is the largest degree terms in the numerator and denominator. And the horizontal asymptote in that case is the ratio of their coefficients, which for this made-up example is 5/4. Okay? And then the last case is when the numerator degree is smaller. In that case, the asymptote is 0. Okay, so for this function, the degree of the numerator is greater than the degree of the denominator, so there's no horizontal asymptote, which means that statement 1 is true. Okay. All right. So the vertical asymptotes are located at the zeros of the denominator that are not wholes. Okay. So when I say zeros, I mean the values for which the denominator is 0 that are not also wholes. So let me expand on that. So suppose we have some function x minus 1 times x plus 2 in the denominator, and the numerator is x minus 1 times x plus 3. So the zeros are the values for which this denominator is equal to 0. So that would be x equals 1 and x equals -2. However, I do have this like extra stipulation. The zeros cannot also be wholes. If you remember, wholes occur when both the numerator and the denominator have a value of 0. So in this case, if x is equal to 1, the numerator is equal to 0, and the denominator is equal to 0. So 1 in this case can't be an asymptote because it's a whole. So -2 is our only asymptote. Okay? So that's a trick to keep your eye out for. So before I can officially say that 4 is an asymptote, is a vertical asymptote for this problem, I have to factor the numerator. And if I factor the numerator, I get x plus 1 times x plus 1, and the denominator factors to 2 times x minus 4. We can see that 4 results in the denominator being 0, but it's not a whole. So indeed, f of x has a vertical asymptote. So they didn't try to trick you for this problem, but that's totally something they could do. And then lastly is slant asymptote. So a slant asymptote only occurs, so going back to our nomenclature of the degree of the numerator is n and degree of denominator is m. It only occurs when the degree of the numerator is equal to m plus 1. So if you have like some x to the power of 4 divided by x cubed, yeah. And the procedure for that is you do long division, and then the slant asymptote is equal to the quotient of the result. Okay? In this case, we don't actually have to find the slant asymptote, we just have to check, is the degree of the numerator 1 greater than the degree of the denominator? The answer is yes, because we have a degree 2 polynomial in the numerator and a degree 1 polynomial in the denominator. So 3 is true. And the last statement is actually pretty easy. It says the x-intercept of f of x is -1, 0. All we have to do is plug in -1 and then see what's the result. And if it's 0, then we can say the statement is true. So plugging in -1, I get -1 squared is 1 plus -2. It's equal to 0. So statement 4 is also true, which means that the answer to 8 is F, all of the above. Okay, moving on to question 9. Question 9 says the rate of growth of a population of bacteria is given by dp dt equals 6t. Okay, and it asks, where p is the population size and t is time in day. The initial size of the population is 2,000. What is the population after 50 days? Okay. So for this question, so we're given dp dt equals 6t, and the way to find p would be to take the integral. Yes. But taking the integral is a little bit, there's a few additional things to consider. It's not just taking the antiderivative of 6t. So the integral is bounded, and we have dp dt from a, the integral from a to b of dp dt is equal to p of a minus p of b. So I'll talk about an easy mistake we could make with this. Okay, and I technically need a dt over here. This is basically the fundamental theorem of calculus. Okay? So in this case, our lower bound is 0, t equals 0 days, and the upper bound is 50. dp dt is equal to 6t, and we have p of 50 minus p of 0. So p of 50 is equal to the integral from 0 to 50 of 6t plus p of 0. So the easy trick easy mistake you can make here is forgetting this initial condition. Yeah, that's just something you have to be aware of. The initial condition isn't always 0, and once we solve, you'll see that one of the answers is, one of the wrong answers is the answer you get when you forget the initial condition. So never forget the initial condition. Okay, from here it's not too bad. We need to first find the antiderivative of 6t, and to do that, all we need to do is use the reverse power rule. So the antiderivative of 6t is 3t squared, evaluated from 0 to 50, and the initial condition is 2000. Okay, now I just plug my numbers in. I get 3 times 50 squared plus 2000, which is equal to 7,500 plus 2000, which equals 9,500. So the final answer for 9 is F. And like I said, if you forgot your initial condition, you'd get D. So never forget your initial conditions. All right. Okay, moving on to question 10. Question 10 says, find the maximum possible volume of a right circular cylinder with surface area of 6 pi feet squared. And it says, if a right circular cylinder has radius r and height h, its volume is pi r squared h, and its surface area is 2 pi r squared plus 2 pi r h. So, in this case, we're given two variables, right? We're given pi is not a variable. We're given r and h, and they tell us some property of our cylinder. And so what we want to do is we want to solve for either r or h in terms of the other variable. Because what that's going to allow us to do is then we can plug it back into our formula over here, and then we'll have a function of just one variable, and we can calculate the value that maximizes / minimizes that value. Okay, so we're given that the surface area is 6 pi, and the formula for surface area is 2 pi r squared plus 2 pi r h. So I'm going to divide by 2 pi on both sides to get 3 equals r squared plus rh. And in this scenario, I have r in 2 locations but h in only 1, so it's going to be easier to solve for h. If I solve for h, I get 3 minus r squared divided by r. Okay, so now that I've solved for h in terms of r, what I can do is I can plug it into my equation for volume. And the reason I'm plugging it into my equation for volume is because the answer I want is the maximum possible volume. So first, before I go about finding the maximum possible volume, I need to find an expression for the volume. Okay. Oops. Alright. So pi r squared, the h becomes 3 minus r squared times r, which is pi times 3r minus r cubed. Okay. So I have an expression for v, and now I have to do something from here. Anytime you see maximum or minimum, most or least, what you want to think is you should think derivative, because the maximum and minimum values of a function are located at the locations where so the maximum and minimum values of some function f of x is going to be located at the values where f prime of x is equal to 0. Those locations are called our critical points, if you remember. So to find the maximum volume, what I need to do is I need to find the derivative of the volume. And that's not too bad. All I have to do is use the power rule. So I get 3 minus 3r squared. And then I have to set this equal to 0. Okay. And if I solve for r, I get r is equal to -1, +1. And since this is a geometry question, you should note that it's not possible to have a negative radius. So the radius that maximizes our value is r equals 1. And all I have to do now is plug r back into my expression for volume. So good, volume equals pi times 3 times 1 minus 1 cubed, which equals 2 pi. So that means that the answer for 10 is A. Okay, moving on to question 11. Question 11 says, find the right Riemann sum that approximates the area under the curve of y equals square root of x plus 5 on the interval 2 to 12 with 100 rectangles. Give the answer in sigma notation. Okay, so let's just quickly recap what a Riemann sum is. So a Riemann sum is an approximation of an integral. So we draw rectangles of equal widths with one end of the rectangle on the curve. So in this case, the left side of the rectangle is on the curve, so this is called a left Riemann sum. Okay, and then the right Riemann sum would look like this. Okay, I'm doing my best. And you can also have trapezoidal sums. I guess I can draw that too. Okay, I think that's how you spell trapezoid. So it looks something like this. Basically, you connect the left to the right. You make a trapezoid. Okay. In this case, what we want is a right Riemann sum. And so we have to figure out a couple different things. All right. So first thing you'll notice between all of these answer choices is that we have a 1/10 I. And that's because we have 100 different rectangles across an interval with length 10. So we're going to be incrementing by 1/10 for each point. Okay, so let's try drawing out our right Riemann sum. Okay, let's say this is 2 and let's say this is 10. Okay, and maybe I'll draw this rectangle in a different color. Okay. All right. Okay. Yeah. So, if this is I/10, this length is 1/10 over here. For each consecutive rectangle, I need to multiply by I for the next rectangle. So first, let's figure out, is I going to be 0 or is I going to be 1? And since we're doing a right Riemann sum, on our first rectangle, we want to add 1/10. So that means that our lower bound should be I equals 1. Because if our lower bound is I equals 0, then we're actually going to be taking this height over here, and that would be the bound that we'd use for the left Riemann sum. So since this is a right Riemann sum, we're going to use I equals 1. And the end will be I equals 100. You'll notice that for all of the, oh, never mind, I guess. So options D and E are from I equals 0 to 100. That's definitely incorrect because that's adding up 101 integrals because the summation is inclusive. So it's going to calculate this value for I equals 0, 1, 2, 3, all the way to 100, and that's 101 different sums. So that should immediately stick out as, like, that's a wrong answer because we're only adding up 100 rectangles. And since this is a right Riemann sum, we want our bounds to start at I equals 1. So according to that, we can rule out A and we can rule out F. Okay? Next, we need to multiply by 1/10 because that is the width. That's the width of this rectangle. And then now we need to figure out an expression for the height. Okay? So the height is going to be our given value of x plus 5. We just have to plug in something here because the height is going to be the value of our function. And since we're starting at 2, we need to add a 2. And then we need to do 2 plus the number of rectangles we've done so far, divided by 10. So actually I should word that differently. It would be I times 1 over 10. The reason it's I times 1 over 10 is because after I've done 3 rectangles, I need to add 3/10 to get the height of the third rectangle. Okay, so then if I simplify this, I get 1/10 times 7 plus I over 10. And that is equal to B. So the key difference between our remaining answer choices is that we have a 5 over here, and we have a 7 over here. 5 would be correct if we were starting from the interval, if we were doing the interval 0 to 12, sorry, 0 to 10, but we're doing this interval 2 to 12. So we need to account for that, and we need to add this extra 2. And I just realized my diagram was wrong before. This should have been a 12. Okay, so that's why the correct answer is B and not C. Okay. Moving on to question 12. Question 12 says, find the x-coordinate of the point on the graph of y equals 5x minus 1 that is closest to the point -1, 2. Okay, so let's say that our point has the x-coordinate a. That means that the y-coordinate must be 5 times a minus 1. And we want to minimize the distance between a 5a minus 1 and -1, 2. So what we can do is we can rewrite distance as a function of a. And so we can do this using the formula for distance. Basically all we do is we subtract one x-coordinate from another and square it, and then we add the difference of the y-coordinates and then square that too. So maybe I'll write it. The distance between 2 points x and y is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. So in this case, my x1, y1 is a 5a minus 1, and my x2, y2 is negative 1 and 2. So that's how I got this expression over here. Okay, and so we want to minimize d. And notice that since we have a square here, this value will always be positive. So it also suffices to say we want to minimize d squared, which is equal to a plus 1 squared plus 5a minus 3 squared. Yeah. Because d, we know d is always going to be positive, it's just a little easier to get rid of the square root sign and instead consider minimize d squared. Because if we minimize d squared, we automatically minimize d as well. Okay. So, what I'm going to do next is I'm going to expand all this out, and I get 26a plus 2 minus 26a squared, sorry, minus 28a. Okay, I'm trying to do this in my head, but maybe it's better to write it all out. So the first function expands out to a squared plus 2a plus 1 plus 25a squared minus 30a plus 9, and this is all equal to 26a squared minus 28a plus 10. Okay, so d squared is equal to this. And so, like I said, we want to minimize, and anytime we hear minimize, maximize, least, most, you want to think derivative. And why? Because if you find the derivative, you can find the critical points of a function, and the critical points tell you where minima and maxima are located. And if you remember, critical points are values where the derivative of a function is equal to 0. So that means we need to find the derivative of the expression that we got for d squared. So if we take the derivative of this, we get 52a minus 28, and we want to set that equal to 0. Okay, and now if I solve for a, I get 7/13. So that means that 7/13 is our critical value, and that is the x-coordinate of the point on the graph of y equals 5x minus 1 that is closest to negative 1, 2. So our answer is B. Yeah.